This video is intended to help introduce you to the idea of projectile motion launch at an angle in terms of solving problems. So we looked at some of the graphing and now we want to actually do some problem solving. So the problem solving process is very similar to the ones that we did with the horizontal launch in that we're going to set up our givens chart in the exact same way we did before. So I'm going to go ahead and do that. On your notes, you should do the same. So we've got delta x, or the displacement in the x, the initial velocity in the x, and the acceleration in the x. Okay, so that's just talking about the motion horizontally in the x direction. We're going to do the same thing in the y. So we've got delta y, initial velocity in the y direction. Usually I write that VIY, sorry about that, and AY, okay? So same kind of deal that we did before. The only difference, as I mentioned a couple days ago, is that instead of launching from right here, which is where we had it before with our initial velocity like this, now we're launching way over on the other side. So this is kind of like kicking a soccer ball or kicking a football, hitting a golf ball, throwing a ball, whatever. Imagine any sort of projectile that's going to go up and then come back down. So some of our givens are exactly the same as they were. In fact, the acceleration in the x direction is still going to be 0. Again, we're ignoring air resistance. We're making sure that there isn't a little jetpack on that object that's being projected, and the acceleration in the y direction is still going to be negative 9.8 meters per second squared. So those two always stay the same. Same for both types of projectile motion. The thing that is different now, though, is that the initial velocity is no longer just in the x direction. As you can see from the picture that we've looked at, the initial velocity now has an angle. So the reason that we took a little time between the horizontal launch and this launch is because we had to figure out how to do vectors a little bit. So if you look at this picture here, you can see that initial velocity vector that goes up like this, okay? It has some part in the x direction and some part in the y direction. So just like we did with vectors, we're going to break this into two pieces. So I've got my initial velocity vector. I'm going to do part of it in the x direction. I've got Vx, okay, and that's the initial velocity in the x direction. And now I do have some initial velocity in the y direction as well. Okay, so in order to figure that out, we do the same kind of process that we did with vectors. So I'm going to mark that angle of theta, and we see that we have a nice little right triangle here. So my initial velocity, I'm going to call that Vi instead of V naught or VO, is the hypotenuse. You can see that the Vy, or the initial velocity in the y direction, is our opposite side. And the initial velocity in the x direction is our adjacent side. So from this, we can use our sine, cosine, and tangent. So we're going to remember SOHCAHTOA. And in order to find the initial velocity in the x direction, we notice that that's the adjacent side, and we know the hypotenuse because we're going to know the initial velocity of the launch. So I'm going to write down the cosine of theta. We're going to remember that's the adjacent over the hypotenuse. So adjacent over hypotenuse. And then if we plug in some values here, that cosine of theta, the adjacent is the initial velocity in the x direction. Remember, because we said the x and the y are completely separate, so we just need the velocity in the x direction. And the hypotenuse is that initial velocity overall. That's how fast it was launched, okay, the speed, and then we're just breaking it up into two pieces. In order to figure out the initial velocity just in the x, I'm going to multiply by Vi on both sides to get the denominator out, okay? And so then I can say that Vx, the initial velocity in the x direction, is equal to that initial velocity overall times the cosine of theta. So every time you do this, we're going to need to find both the angle and the initial velocity to find that initial velocity in the x direction. We can do the same thing in the y direction. We're going to use, this time because it's the opposite, we're going to use the sine. The sine of theta is equal to the opposite over the hypotenuse. Okay, so we can plug in the sine of our angle theta is equal to Vy initial divided by that initial velocity. Again, multiplying by VI on both sides. Those VI's cancel, and we've got VY initial is equal to VI times the sine of theta. So if I zoom out a little bit, we can now plug those things in to our givens chart, okay? So when you do this, instead of just plugging a number in like we normally have, we can say that the initial velocity in the x direction is going to be equal to VI times the cosine of theta, and VY initial is going to be VI times the sine of theta, okay? These are not on your equation sheet. This is one of those things that you will have to know and to understand so that you can solve these problems. One last thing to kind of keep in mind, delta x we sometimes call the range of the projectile, how far it went in this direction here. Right there, that would be the range. Sorry, that's a little bit hard to see. And delta y, if you talk about the overall process from launch to when it hits the ground, that is equal to 0 meters because it goes up and then comes right back down. It's the displacement. So again, if you're talking about the whole path, and only in the whole path, you can say that the displacement is 0, okay? Check out the next video and we'll do a couple problems.